Welcome back to Calculus 1. In this lecture, we're going to introduce the most important differentiation rule, the chain rule. Now, if you think back to what we've covered recently, we had two previous differentiation rules, the product and quotient rules, which are very important, but for several reasons, this new rule, the chain rule, is actually more important. We're going to see it pop up in more examples. You'll see it pop up likely a lot in your physics courses, some of your engineering courses, and for some of the topics that we'll be getting to in the lectures following this one. So the next few lectures will all relate back to the chain rule. So this rule, the chain rule, it's kind of foundational for many different aspects of our course and beyond. All right, so let's get into it. Let's start with kind of some conceptual questions just to focus on, let's say, 3 of them here. What I want you to think is, how would you calculate the following derivatives here? I don't want you to tell me or respond with what the derivatives are, just what rules would you use to find the derivatives of each of these 3 functions? All right, if we take a look at the first one there, e to the x times sine of x, we have a product, so we use the product rule. Seems pretty straightforward. The second example, we have e to the x divided by sine of x, a fraction or quotient, so we use the quotient rule. All right, now e to the x and sine of x in those 2 previous combinations were combined in a very simple way. We multiplied or divided them. Well, what do we do with this last one? E to the x and sine of x are combined, but they're combined with a kind of a 5th unique operation for functions, what's called a composite function, where we plug one function into another. And the product rule won't work for this, nor will the quotient rule. So here, the derivative of e raised to the sine of x, that is something that we currently cannot answer. So we need to come up with a new rule, a rule to differentiate composite functions, and that is exactly what the chain rule is for. So product rule is for products, quotient rule is for quotients, the chain rule, that's for composite functions. Notice in that notation, that's not multiplication, f times g of x, but that's f of g of x. G of x is plugged inside of f of x in that notation. Okay, now before we get into kind of the rest of this lecture, which we're going to take our time and split this into 3 parts, just to make sure you're comfortable, we'll do a kind of brief review of composite functions, the different sorts of questions, and then how we'll relate that to what we need for composite functions to apply the chain rule. All right, so let's get to a very brief review of composite functions, as you might have covered it in your pre-calculus course. If you find some of this looks unfamiliar, definitely follow up with me or your professor during office hours for that. This is just intended to be a very brief overview of composite functions. Okay, so this notation hopefully looks familiar. The circle there, that operation, that's what we call the operation of a composition or composite function. So that's f composite g of x, and we write this as f of g of x, plugging g of x inside of f of x. All right, now hopefully the notation here makes sense and is familiar. We're going to refer to f of x on the outside there. We'll refer to that as the outer function, since it's on the outside. And then we'll refer to g of x as the inner function, since here, notationally, g of x is inside of f of x. Okay, so we'll be referring to inner and outer a lot. Let's just take a look at a very basic question. This would be probably the simplest sort of question you could ask or be asked to answer in your pre-calc course when covering composite functions. You're given f and g, the 2 functions, and you're asked to find and simplify the composite function. So just to kind of test how you're coming into this course, pause and give yourself just a little bit of time to answer this question. Not a calculus question, but we'll be building up to that very shortly. And this will give you a sense for how much you might need to review coming into this lecture on the chain rule. So pause and give yourself an attempt at this. Find and simplify f of g of x for those two functions provided there in the example. We'll check in about a minute. All right, so let's go through that. We're going to replace all x's in the outer function. The outer function here is f. Every x is going to be replaced with g of x. Now, since we have x in two spots, we're going to replace each of those x's, that's our input variable, with g of x, which is 2x minus 3. Okay, so hopefully you're comfortable with that. We get 2x minus 3 raised to the fourth power minus 2 times 2x minus 3 plus 1. All right, you could multiply that all out. That's going to take a while. This is just one question that we're going to build off of. Given the two functions, f and g of x, find and simplify the composite function, f of g of x. Now this question or example, that's kind of the simplest sort of question you would be asked in your pre-calculus course. It's very computationally challenging. Usually for pre-calc students, the algebra skills need to be built up a little bit. And you can see there expanding 2x minus 3 to the fourth power. That would take a while. Okay, what we're interested in for whatever this thing called the chain rule is, which we'll be getting to, we need to address the opposite or inverse question. So the question written there in the middle of the screen is, given two functions, find the composite function, f of g of x. The inverse or opposite question is basically, given a function, that's a composite, identify and find the outer and inner functions. So instead of given the pieces and combining them together, we're given the answer and asked to find and split apart the pieces, f and g. And this is computationally simpler, but conceptually a little more challenging. So let's focus on the inverse or opposite question, which is what we're going to need to be able to understand to apply the chain rule. All right, and what we'll be looking for in this inverse or opposite question is, given a function h of x, we're going to try to view it as f of g of x, and we're just going to basically try to identify what the outer and inner functions are and determine f and g. All right, when you're ready, we'll take a look at several examples of that. All right, now this question is one of the sort of questions in my pre-calculus course where I find students, they either get it or they struggle greatly with it until a few examples are gone through. So I'd like you to try this. Here we're given the answer from our previous question in some sense. So we're given the composite function, and we want to identify the outer and inner functions for this. So what would be an outer function f of x and an inner function g of x such that f of g of x gives this function h? Pause and see if you can write down a pair of functions, an outer and inner function that would work. All right, one pair that will work. We're going to take our outer function to be square root of x, since that function h has a square root on the outside. And then our inner function g of x, we'll take it to be the inner quantity inside the square root. So we'll say g of x is 3x squared plus 1. All right, notice if we plug g of x into f of x, we get our function given there, h of x, which is the square root of 3x squared plus 1. All right, notice there's really no elaborate calculations we're doing here, but we're just trying to view a given function as a composite function. All right, as it turns out, this is not the only pair of functions that works. See if you can write down a different pair of functions for the outer function f and inner function g of x. Right, now they're really not that different, but they are technically different. Here's another pair that would work. Let's say our outer function is the square root of x plus 1. And if we plug g of x into that, replacing the x in the outer function, we'd have to have g of x to be 3x squared. And notice if you plug g into f there, we get our given function h of x. So what we have here are two pairs of functions that work. Let's just go ahead and write down a third pair so you can see that there's really not a single pair of functions that works for this question. There's many different possible pairs of functions that work. All right, now between those three pairs of functions, in order for us to apply the chain rule, we're going to want to identify the choice with the simplest outer function. And if you take a look at those three pairs of functions, just take a look at the outer functions, f of x. It goes from square root of x to square root of x plus 1 to square root of 3x plus 1. All those pairs, in order, the outer function is gradually getting more complicated. Now, while that works, as those all being acceptable answers for the pre-calculus inverse question, we're going to want to use the pair with the simplest outer function to apply the chain rule. And the reason why we want that is take a look at the outer function there, f of x, square root of x. We can rewrite that as a basic power, x to the 1/2 power, and that is a function for which we already know its derivative by applying the power rule. So in all these questions, when we get to applying the chain rule, we're going to want to identify our function as a composite such that the outer function is as simple as possible. All right, let's take a look at a second example. This one, I'll pause and give you an attempt at it. You might feel a little more comfortable having gone through the first example. So we'll check in about a minute. Identify an appropriate outer and inner function. So find an f of x and a g of x that would work. We'll check in about a minute. All right, now one of the keys or clues here to look for is parentheses. And what's inside the parentheses, we can usually take that to be our inner function, g of x. What's on the outside though? A 5th power. And we can't just have it as the outer function as just a 5th power. We need an x in there. So we'll say our outer function is x to the 5th. The inner function, what's inside the parentheses, we'll take it to be 1 plus sine of x. All right, and again, notice here, referencing in red, kind of right above, we want to choose the choice for the pair of functions with the simplest outer function. X to the 5th is a simple function. We can differentiate x to the 5th using the power rule. All right, let's take a look at one last final example, just to kind of get you comfortable with notation we're getting into. Let's say the function here, h of x, is cosine cubed of x. I'll give you a hint in a moment, but see what you can do with this. This will really determine how well you understand notation, trig functions, different powers, notations for powers of trig functions, which might have been a while ago in your pre-calculus course. We'll check in about a minute. All right, now this might be a little bit more difficult, so let's rewrite this. The notation here, cosine cubed of x, what that really means here is cosine of x, and that whole quantity is cubed. Now, if you rewrite that, now it might make it a little more obvious what your outer and inner functions are. We can say our inner function is cosine of x, and the outer function, the third power, we'll say the outer function f of x is x cubed. All right, now notice by rewriting it, you might feel a little more comfortable identifying your outer and inner functions, but we're going to be seeing powers of trig functions a lot kind of at this point of it in our course and beyond. So just make sure you're comfortable with the notation there in example 3, cosine cubed of x, which really means cosine of x cubed. All right, now make sure you understand what's going on here with this inverse or opposite question. Given a function, identify it as a composite and determine the outer and inner functions. If you feel comfortable with these examples here, identifying f and g of x, then you're well on your way to being able to answer a question applying the chain rule with our approach called divide and conquer. All right, when you're ready, let's get to stating the chain rule. All right, and here it is. Again, the chain rule is a rule for differentiating composite functions. So we're usually going to write that as y is some composite f of g of x. We're going to refer to f as the outer function and g as the inner function. All right, and we're not going to state it with proof, but the derivative for this composite function, y prime, equals f prime of g of x times g prime. And notice the original function is a composite. There is still a composite here in the derivative. The f prime of g of x, that is a composite function. All right, now this is the statement of the chain rule, which doesn't really tell you what's going on with it. So let me kind of write out in pieces below there what this chain rule kind of statement says. So we have f prime, that's the derivative of the outer function. Notice inside the function parentheses is g of x. So we can say f prime is evaluated at the inner function. And then we multiply by g prime, which is the derivative of the inner function. All right, and you'll kind of hear me through questions as we go through it, kind of saying the chain rule, we apply it, we differentiate the outer function, plug the inner function in, and then multiply by the derivative of the inner. And that's all kind of written down there, which it's helpful to kind of keep that in mind as we go through our first set of examples, which we'll be getting to shortly. All right, now this is the version that we're going to apply most often, but there is another version which is different notation, but it's usually a little more complicated in practice to apply. Now the notation changes. We still have a composite function, but it's just how we reference the notation for one function being plugged inside the other. So this alternate version, let's say we have y as a function of u. So y equals f of u. And the u is a function of x. So we'll say u equals g of x. All right, this is a composite function. F is a function of u, but u is a function of x. So we have a function inside a function. All right, notice if you plug that in, u equals g of x, we get exactly the original notation for our function, f of g of x, written above. All right, this new version for the chain rule, which is just kind of rewriting this in different notation, we're using here differential or Leibniz notation. We're going to say if y equals a function of u, where u is a function of x, the derivative of y with respect to x, that's the dy over dx there, that equals the derivative of y with respect to u, dy over du, times the derivative of u with respect to x, du over dx. Now, this really is the same thing as the version above, but it's a little more complicated to understand for most students. So let's just kind of see in non-differential notation, switching back to prime notation, how this is consistent. So let's say we have y as f of u, dy over du is just f prime of u. We differentiate y with respect to u. All right, to the right, let's say u equals g of x. Differentiate that with respect to x. Then the derivative du over dx equals g prime of x. All right, let's rearrange this new version there, kind of written to the left in differential notation. Let's just plug in the pieces so you can see that it's consistent with the basic version stated above. We're going to replace dy over du with f prime of u, and we'll replace du over dx with g prime of x. All right, that looks a little closer to the first statement for the chain rule above, but we have the variable u in there. Well, just replace u with g of x, and we get the exact same version as above. All right, now these two versions are only different in terms of notation, and we'll be relying on that kind of through different parts of the calculus sequence. So make sure you're comfortable with understanding both versions, but in practice, we're going to primarily apply that first version, y prime equals f prime of g of x times g prime of x. All right, definitely copy these down, pause if needed, and we'll take a look at a few examples basically throughout the rest of this lecture, which will split into 3 parts. When you're ready, we'll get to kind of our first example. All right, let's go through this one together. So this question is pretty straightforward. We're given a function and now asked to find the derivative. The only difference is now we're going to be using the chain rule. We know how to apply the product rule. We know how to apply the quotient rule. We're learning right now how to apply the chain rule, a rule to differentiate functions with inside functions. Technically, we call that a composite function. All right, let's go through this slowly. First, we're going to have to identify the function as a composite. That goes back to our inverse question, which we did 3 examples for. So we did this as one of our examples, the first one. So this shouldn't be too bad. This is the first step in us applying divide and conquer. All right, so for that function, we're going to say the outer function is x to the 1/2 power, square root of x. And the inner function is 3x squared plus 1. All right, what we're doing here is splitting the original problem into simpler pieces. We're viewing the pieces as coming from a composite function, f of g of x. That's the only difference with divide and conquer here. F and g are not factors. F and g are not the numerator and denominator, but now f and g are the outer and inner functions respectively, thinking of our given function as a composite. Now, even though we're going through this together, I'd like you to make an attempt at calculating these 2 derivatives. If you can do that, you're well on your way to completing your first example, applying the chain rule. So calculate f and g prime, those derivatives. We'll check in about a minute. Okay, so we just have to apply the basic power rule here. So f prime should come out to 1/2 times x to the negative 1/2 power, applying the power rule. Bring your power 1/2 down, and then you get x now to 1 power less, 1/2 minus 1 gives negative 1/2. All right, and if you differentiate g of x, you should get g prime as 6x. All right, all we have to do now is combine these pieces together. Now we're combining them together using the chain rule. F prime of g of x. So we plug g of x into f prime, and then we multiply by g prime, which is the derivative of the inner function. All right, if we plug all that in, we get our answer for y prime, the derivative, as this. And just make sure you're comfortable where the pieces are coming from. 1/2 times 3x squared plus 1 to the negative 1/2 power. That is f prime of g of x, plugging 3x squared plus 1 into f prime. All right, and the 6x at the end, that's multiplying by the derivative of the inner, multiplying by g prime, which we found to be 6x. All right, now this can be cleaned up a little bit. Notice you have a kind of a factor of 1/2 and 6. 6 divided by 2 will give 3. And we can even rewrite this. I'm not claiming it's going to be any simpler, but for various different purposes that we'll be getting to throughout the calc sequence, you might want to express this without negative exponents. So we can put the negative 1/2 power, we can put that as a factor in the denominator. And a 1/2 power, we can think of that as a square root. Okay, so we get kind of our answer here, rewriting this as 3x, then divided by the square root of 3x squared plus 1. All right, now that's applying the first version for the chain rule. Let's go ahead and apply the second version, which is a little more complicated to apply in practice, but we'll take at least one look at an example applying this just for completeness. All right, so we're going to use this new alternate version written in differential Leibniz notation. All right, so we're going to identify our outer function as the square root, but we now say square root of u. And we're going to identify the inner u as a function of x. So we'll say u equals 3x squared plus 1. Now we should still get the same answer as before. It's just how we arrive at it that is a little different. All right, so we have our function, y as a function of u. So we'll say y equals u to the 1/2 power. And we'll identify u as a function of x and say u equals 3x squared plus 1. Let's calculate each of those derivatives, applying the power rule. The derivative of y with respect to u should be 1/2 times u to the negative 1/2. Very similar to our application of the power rule in the previous version. And if we differentiate u, we still get 6x for the derivative of u with respect to x. All right, now how do we get our answer for the function's derivative? Well, we multiply dy over du by du over dx. Now we can simplify it in a similar way. Notice we still have a factor of 1/2 and 6. 6 times 1/2, or 6 divided by 2, would be 3. And to make our answers look exactly the same, let's express our derivative only in terms of x. So we'll plug u back in as 3x squared plus 1. All right, and if we do that, we get exactly the same answer. It's just how we identify our function as a composite and different notation. All right, now that does it for our first example. We're going to kind of end part 1 here. Part 2 is going to immediately pick up with more examples.